Welcome back to Gabversity, where facts don't care about your feelings. And here we are. We now are doing some quick astronomy. And here is the question, once I can enter in my password, because this phone, stupid freaking laptop, goes to sleep every 5 seconds, and it drives me nuts. Oh, we're here to save your battery, yeah, and cause me freaking grief in the process. All right, so as you remember, hello, the new story for hello, good morning. For Gabversity, the new motto for Gabversity is go fact yourself. That's my new one. And I'm gonna paint something. I'm gonna probably make some coffee mugs with Pompous on there with a line saying, go fact yourself. Go fact yourself. That's too good. All right, so here is our question to solve. Our question to solve is this. And I was instead of trying to learn the lecture, what I do is I try to create some basic mathematical equations that fit the model, and then I test them, and that worked. So finally, we're good to go. So the brightest planet in our sky is Uranus. No, that's not true. I'm kidding. It's Venus. Of course it's the brightest because women are from Venus. All right. Which has an apparent magnitude of -4, right? Apparent magnitude of -4. That's different to absolute magnitude. Absolute magnitude is the brightness of something when you adjust for its location. Because as you know, if you have a light in your room, when you walk away from the room, the light is less bright, obviously. But you have an absolute brightness, which is a way that you know how bright something is compared to a light in another room. Okay. The apparent magnitude is -4 when it is 1 astronomical unit away from Earth. What's 1 astronomical unit? So here's Venus, here's Earth. We have 1 astronomical unit. Should I draw it for you, or can you can figure it out? All right. 1 astronomical unit, which is the average distance from the Earth to the Sun. Good night, brother. Which is 8 light minutes on average away. So if the sun blew up, you wouldn't know about it for 8 minutes. Because that is the speed of causality. That is the speed at which things happen in this universe. 299,792 kilometers per second or meters per second. I think it's kilometers per second, yeah. Because it's 186 million miles per hour or something. That's pretty cool, right? Can you imagine? That you can travel, if you travel at the speed of light, which you can never do, you could go around the Earth in 1 second 7.5 times, which is crazy. All right. So how much fainter would Venus look from 5 parsecs away? And 1 parsec is approximately 206,000 astronomical units. So the average distance from the Earth to the Sun multiplied by 206,000 times. That's 1 parsec. And if it's 5 parsecs away, how bright would Venus look? What would be the apparent brightness of it? Well, what I did was I created a little equation. And the equation is this. M2 equals M1 plus 5 log D, right? D is the distance, and the distance, relative distance away, is 5 parsecs, right? But compared to, we have to put it into astronomical units. So, hey, Dr. Supernova. All right, so 5 parsecs is 5 multiplied by 206 approximately thousand astronomical units, and 1 astronomical unit is the average distance between the Earth and the Sun. Okay. So where we are, if you look at the sun, don't look at the sun. If you see the sun, wear some sunglasses. That's 1 astronomical unit roughly away, right? Okay, so hello, welcome back. So 5 parsecs away, right? It's going to look a lot fainter, and that's the ratio, right? 1 compared to 5 parsecs. That means 5 by 206,000 astronomical units. All right, so what we'll do is, I'm going to draw it for you. So basically, here is the Earth, and here is Venus, okay? And from Earth, and this is Venus, all right? The distance, 1 AU. So at 1 AU, right, the brightness, apparent magnitude, right, apparent magnitude, M2 equals, oh sorry, M1 equals -4. All right? That's the apparent magnitude, so relative magnitude. But if we were to go, whoa, all the way out, right? So if we were to go, and this is not the scale, obviously, if we traveled dot, 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 here, which is 5 parsecs, which is 5 times approximately 206,000 AU, what would the brightness be? Brightness, so what's M2? What would the brightness be out here? Well, here is the equation. The brightness would be -4 plus 5 log the distance. And the distance is that. So you chuck that in. Small. Yes, write that in your exam. Small. All right. So if you do that, then the answer here, put it in your calculators, and then I'm going to tell you the answer. So this isn't an ethics class. No, it is not. That was the last one. This is now the astronomy class. Funny. All right, so I'm going to get you, that's -4, and the distance is 5 times 206,000 AU, right? So that's the distance ratio. So put that in there and see what you get. Let's see who gets the answer, right? Get your calculator, give it a go. I'll give you 30 seconds. Let's see who can do it. Who can do it? All right, I'm just watching. Fair enough. Thank you for telling me. Otherwise, I would have been sitting here for hours. All right, the answer is 26.1059. So, in other words, we put -4 plus 5 log, and that's log base 10. Just chuck it in your calculator. And D, which is 206,000 astronomical units by 5. Right? So 5 parsecs, which is 5 of these, right? Because remember, that's 1 AU, and that's 5 times 206,000. So that's the ratio, right? 1 to that, right? So we chuck that in there, and we put -4. Satan says, man, people have the funniest names. And that answer is 26.1059. Here's another question. How much fainter would it be? You lost me at 5 log D. You had me at hello, lost me. 5 log D. Basically, you just put that in your calculator. Log, it's a function. I explained this in the astronomy lecture like 3 lectures ago. Math is like Chinese. And to me, Chinese is like math. Too funny. 5 log, yeah. You got to put in your calculator 5 times log times the distance. My Mandy. Always a pleasure. All right, that's fun. All right, so here's the next one. How much fainter would it look? How much fainter would Venus look? How much fainter? Chinese is a lot easier. Oh, you're smarter than me then. How much fainter? The more you move away from a light, right? Here is the formula. The more, so here is your light source. We'll just make it a light bulb. Ding! That's a really bad light bulb, isn't it? Yeah. I have no idea how to draw a light bulb. Now it sort of looks like a hairy hand. A hand with lots of fingers. I don't know. That's the worst light bulb in history. Oh my God. All right. Here is your distance. This is your distance. Now, if your distance doubles, so this is D1. If your distance doubles, right, it works on a squared ratio. So let's assume this distance equals 1 meter and this one equals 2 meters, right? Then the ratio, which is double, that means it's going to be, how many times fainter? It'll be 2 squared, which equals 4. So in other words, if you double the distance, then you 4 times the faintness. Micro mathematics, welcome. Right, you double the distance, right, and it's squared. So if you triple the distance, let's say the distance away is tripled, then it's going to be 9 times fainter. If you go 4 times the distance, it's going to be 16. So if you were to draw this graph, right, this is distance, and this is brightness, what would happen is that you'd have a parabolic function. So it would look like that, which is interesting because parabolic functions happen to be exactly the shape you need for a satellite dish, a 3D parabolic function. So you get a parabolic function and you rotate it, you get a satellite dish. Because what happens is that allows every light beam coming in to bounce exactly into the focus, which is, if you look at the satellite dish, there's always this little thing raised in the middle. Yeah. All right. So I'll show you what I mean. All right, here is your satellite dish. And you know, it goes inwards, obviously, and I am the worst artist in the world, which is why I do physics, because I can't draw. Right in the middle, the light bounces. Let me draw it side on, because I'm just so hopeless. Right, here is your satellite. Right, here is the focus, and whichever light comes in a parabola, it'll always bounce into the focus. If it comes here, it'll go into there. If it comes there, it'll go into there. It always goes into the focus, and that's one of the brilliant things about a parabolic function. And the parabolic function is normally written like this: x squared equals 4ay. Everyone is an artist. Well, then you'll have to help me find that artist, because I have no idea where it is. Alrighty, so there you go. That is, as the distance moves away from the brightness, you get this, right, in terms of how much fainter it is. Mm-hmm. So how do we calculate this question? Well, it's quite simple. If we have moved this much further away, 5 by 206,000, then we just have to square this number. And if we square it, we'll find out how much fainter it is. So the answer is 1,000 billion, or 1 million million. 1.1 million times fainter. If you go that distance away, that'll become 1.1 million times fainter. So imagine when you look in the night sky, right, at all those stars which are so much further away than this. Imagine how much brighter they'd be if they were in our solar system. We'd probably all burn to death. So there you go, Patriots United, everyone's here. So that ends our astronomy lecture for today. I'm going to leave you with a question, and let's see who can answer this question for our next astronomy lecture. All right, you take this home, right? Whoever answers this gets nothing, because I don't have anything to give you. You're welcome. But at what location, you missed again. I'm doing a quantum mechanics one after this. At what location on Earth is an observer that has the south celestial pole directly overhead? Right? So let me ask that a question. The south celestial pole, right? Where do you have to be on Earth to have it right above your head? Okay, so on the Earth, when you stand, the south celestial pole has to be over your head. I'm going to give you 5 options, and then on our next lecture, we'll see who has the answer. So, option 1, 45 degrees north latitude. Option 2, 45 degrees south latitude. Option 3, at Earth's north pole. Option 4, at Earth's south pole. And option 5, at Earth's equator. So where do you have to be standing on the Earth to have the south celestial pole directly overhead? I'll give you the options one more time, and then who can tell me? Well, now we get to Google it. Oh, I didn't even think of that. Damn it. Well, you 45 degrees north latitude, 45 degrees south latitude, 90 degrees north latitude, which is the North Pole, 90 degrees south latitude, which is the South Pole, or 0 degrees, which is the equator. And we will see you next time on Gabversity, where Pompous says, "Go fact yourself."